if you are not getting things, if you can't understand what is happening, it is totally fine. मेरे साथ भी यही हुआ था. At the start you will be bombarded with a lot of topics. There is lot to learn in ML. So yeah, I've kept today's thing a pretty basic one, and feel free to ask questions. The chat is open. You can just put in the you can ask questions at any point of time. After each topic, I'll try to answer, but if not, then we can move it to the last 10 minutes where we'll have a pure Q&A. And yeah, if someone wants to open their mic also, I think we can give the permissions for that too, right? Okay. Yeah, let me share my screen. Just confirm whether my screen is visible or not, right? Yes, is it visible?
Yes, sir.
Yeah. अरे ये सर रहने दो यार. You can call me Nisarg. I'm not entitled to that post yet. Okay.
Okay, sir. All right.
Yeah, just call me Nisarg. It's fine. Okay. ये बताओ यार, who are the people who have joined here? First year, second year, third year. What's the status?
So second year and third year.
Second year and third year. Ah, nice.
Yes.
Placements are near. It seems, right?
We can say.
Right. Okay. So let's start. Um, एकदम ग्राउंड लेवल से शुरू करेंगे. We'll start with the ground levels of machine learning. So even if a beginner who doesn't know anything about machine learning, he can also stay on the line with us. So yeah. So let me start with the big picture. So here you can see machine learning is vaguely categorized into three topics. One is called supervised learning, there is unsupervised learning, and then there is reinforcement learning. This is a very vague classification. You can have subclasses as well, but I've gone for a very vague classification for the basic purposes. The first thing that we like to point out is what problems is machine learning solving. Was there a problem that could not be solved without machine learning? Is machine learning really a need, or is it just a luxury? So let me see if you can answer this in the chat. Just answer my question. Is it a luxury, or is it a need? Anybody can answer whatever their opinion is there. Okay, I guess blank. Everyone's blank, right? Luxury. Okay. Uh-huh. Okay. Need, right? So a few people feel that it's a need, and a few people feel that it's a luxury, right? So it is midway there. It is neither a luxury nor a need. There is no scenario that is only solved by machine learning, right? You can solve things without machine learning also. There are far we reach the moon without machine learning. Okay, so it is not a need, but it sure makes the tasks easier. It makes them highly efficient. It also makes them some impossible tasks, like let's say I cannot teach a robot to control his movements or control his have his own conscious without machine learning. So it is a luxury at some aspect, but it is also a need for this hour, because we are moving towards self-driving cars, automation, everything is on the way, right? So machine learning has become a need recently, but it is not a need, right? It is moving towards it. It tends to a need, right? So yeah, with that scenario in mind, let's go for what the big picture is basically. So we have three categories: supervised learning, unsupervised, and reinforcement learning. Now, what are these three things? So unsupervised learning, as the name suggests, when you're working and there is no supervision over you, what happens? It is you tend to take breaks, you tend to delay your tasks, right? So similarly, unsupervised learning is basically when your let's say the model is a kid. Okay, so let's say the kid is trying to learn something, but he is not supervised. He doesn't know what the outcomes are. He's trying everything. He's trying to make sense of what is happening, but he is not aware of the outcomes. So that is what unsupervised learning is. It doesn't know what the outcomes are. So common problems and common scenarios in unsupervised learning are clustering methods basically. So yeah, so that is unsupervised learning. Then let's go for supervised learning. What is supervised learning? Now, supervised learning is a advanced version of this unsupervised learning. He's the big brother. Okay, what he does is he knows what the outcomes are because he has already seen the scenarios. He knows what the expected result should be. तो पेरेंट्स से डांट कम पड़ेगी if you know what to do. So supervised learning is like the big brother. He knows what the outcomes are. He'll perform better. He knows what to do, when to do, everything. And common scenarios in supervised learning, you will have is dimensionality reduction, regressions, and classifications. We'll dive further into these classes in the next few slides. And reinforcement learning. Now this is emerging field. It has started way back, but it has come into light in the recent times. What reinforcement learning does is it is the same way how you train your pet. Let's say you're training your pet for doing a trick. What would you do? When your pet does the right thing, you would treat him, right? You would give him a treat, you would give him a biscuit or whatever he likes. So reinforcement learning, it is a way of reward. It is a way of reward system. When the model does what you like, you reward it, and if it does what you are not expecting, you take away the reward or you punish it. So that's the way reinforcement learning works. We'll not be diving too much into reinforcement learning as that is a little advanced topic. We'll cover unsupervised and supervised learning for now, and we'll then go on for some example cases in supervised learning. So any questions up until now? Anything that you want to ask? Anything that you didn't get? What these learnings are, or ये सब कहाँ काम आएगा? Hmm. Okay, we'll do one thing. We'll keep the questions for the last. Let's see. Right. Let's start. So supervised versus unsupervised learning. The same points that I have narrated, we'll reiterate it again. So technically, in technical terms, supervised learning uses labeled data. What do you mean by labeled data? Let's say I have 10 images of fruits, right? One is an apple, there's a banana, there's an orange. So there will be labels associated with each image. I know that this is an apple, but your computer doesn't know this is an apple. Similarly, what is unsupervised learning? Unsupervised learning is basically unsupervised learning doesn't use a label data. It will try to figure out based on the data points. It doesn't have the label knowledge. So what happens is unsupervised learning, because it has the labeled knowledge, it will basically run on a feedback mechanism where you can see whether what it is doing is right or wrong because it knows what the outcome is. Let's say you give him an apple and it says that it is an orange. So that's a wrong outcome. But what if it says it's an apple, so it's the right outcome? So that way you can test the model. The model can find the outcomes through the labeled data. So it runs on feedback mechanism. And in unsupervised learning, it doesn't, of course, run on the feedback mechanism because there is no feedback, there is no labels. It won't know what is happening. So common example supervised learning is classification problems. As you can see here, let's say we have these 4 data points right here, right? And these are a few other data points. Now, because the machine learning model knows that there are 2 different data points, let's say these are the circles and these are the crosses. Let's say I have with each associated data point, let's say the coordinate 10 comma 10, it is associated with a circle. The label is circle, and the coordinate, let's say this is somewhere around 100 comma 100, let's say, and this is associated with a cross. So now the machine learning model, he knows what's the output, right? He knows that at 10 comma 10 there's a circle. It knows that at 100 comma 100 there is a cross. What if it predicts there's a cross at 10 comma 10? He has the labels to verify. He can verify using the labels whether what I have predicted is it right or wrong. But let's say he doesn't have the labels. There is only a single data type that it is constricted to. That is circle, 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 circle. Everything is a circle. So now what this turns into is a clustering problem instead of a classification problem. Here there's a clear boundary that you can view, right? It is basically classifying this as one type of data and this as the other. But here, though it doesn't know what these are, it can still find based on the clusters. Clusters are basically group of data. You can call them groups, clusters, as the normal English language goes, right? Clusters are groups of data. So here it turns into a clustering problem. So we'll start with a few popular algorithms in unsupervised learning, right? K-means clustering is a very, very common algorithm that you will be taught when unsupervised learning comes into picture or clustering comes into picture exactly. So what is this K-means clustering? So let's say I have a few data points that are x's, a few data points that are circles, and a few data points that are triangles. Now, the goal of my machine learning model is to differentiate which is which. I should know that given a data point over here, it should not say that it's a circle. It should either say that it's a cross or even the probability of being a cross should be higher. So now what k-means clustering does is it is heavily based on initial conditions. Now k-means clustering works on the basic principle of distances. The first step is initialize k cluster center randomly. Out of these three clusters, we can just initialize a random data point. Let's say I feel that in the data set there are three clusters. So I initialize three random centroids or centers. Let's say one over here, one over here, and one over here. Now what these clusters try to do are they calculate the distances with each data point that are available. After calculating the distances, it finds the nearest data point and sets that as the cluster. Let's say this is the nearest data point to the A centroid. It will assign it as the cluster. Let's say for the B centroid, this is the nearest data point. So this will get assigned as the cluster. And let's say for the C data point, this is the nearest one. It will get assigned as the cluster. This similar step will be performed over hundreds of iterations or how much ever is required. And each time, as you can see here in the figure, the centroids keep shifting to a place where there is high density. So where the distances are normalized basically. As you can see here at the end of the iteration, the clusters come to a understanding that there are three partitions. There are three clusters basically. So this is what k-means does. It is working through clusters. Now, if you don't understand the exact mathematics right now, it is fine. That is not the goal of this session, because mathematics is necessary, but it will take a lot of time for each and every algorithm if I start explaining the mathematics behind it. Although it is very important, the mathematics is important for you to know how the algorithm works. So we'll be going over the basics, and if you're interested, we can go for the mathematics later on. So yeah, but can you see a flaw in k-means clustering? Do you find or do you see any possibility that it will not perform well in certain situation or whatever scenario it is? Can you see that? I'll give you like 15-20 seconds to just think. What could be the situation where it doesn't perform well? Okay. Uh, One condition could be the initial conditions, as the k-means clustering is very sensitive to the initial conditions. As I said, the initially I say that there are three clusters, but this is an assumption. Unless I know the data very well, I cannot say that there are three clusters or four clusters. So in a data set where there are only three suspectable clusters and I start with five clusters, it is going to give wrong information. It is going to create wrong boundaries. So it is very heavily sensitive to um, the initial conditions. And second thing, it is not very good at non-linear data. Let me show you what does that mean. So what if I give you a data set that is something like this? It is not a linear boundary. If I say this data set, so this is a linear boundary. I can make a linear boundary over here. I can consider these as one cluster and these as the second cluster. So linearly there is a differentiation, but here the two clusters are basically concentric. This is the first cluster and the outer one is the second cluster. Similarly here, this is the first cluster and this is the second cluster. So do you think k-means will figure this out? Do you think this k-means algorithm is smart enough to cluster to make clusters out of these? If you are thinking yes, I'm sorry to say it won't happen, because the k-means cluster, it works really well on linear data, but this is where it misses out. It basically misses out in data where there is non-linearity, non-uniform data which is non-linear. So you will get an output which is something like this, where it is trying to make a cluster like this. This is the first cluster and this is the second cluster. So that is what it will try to do. But by visually we can see, it is clear for us that this is the first cluster and the other one is the second one. But yeah, of course computer is not that smart enough without us. So that's where hierarchical clustering comes into the picture. Now, this is not an exhaustive list. All the algorithms that I'm mentioning here, they are just the tip of the iceberg. It is just the basics and the standard ones. There are a lot more sophisticated and improved versions of these algorithms. I'm just trying to show a difference why each algorithm is important. What is the importance of each algorithm? Why k-means is important? Why hierarchical clustering is important? What was the need for this algorithm to pop up? So yeah. Now, how hierarchical clustering works is it moves from the other way around. K means it starts with three clusters and it tries to uh, move the centroids around and basically convert the whole data into three partitions. But what the hierarchical clustering does is it works on the principle of basically bottom to top, right? So initially there are zero clusters. Initially there is nothing. Now what it does is it will take the two nearest points and make a cluster out of them, as you can see here, and then the next cluster, and then the next two nearest ones make the next cluster, and the next two nearest one make the next cluster. At the end you will be left with a one big cluster. So using this dendrogram, this graph is called a dendrogram. So what it does is, what this graph says is, P5 and P6 emerge to be one cluster at this point. After that, P4, P5, and P6 are one cluster. After that, P3, P4, P5, and P6 are the next clusters. Similarly, here P1 and P2 are one cluster. After the next iteration, P0, P1, P2 become the next cluster. And at the end, all of these combine to become a single cluster. So now where does this help us? Here we can define, let's say your data has three clusters, okay? But it is very hard to visualize large data sets. Here I can show you the graphs and all because it is a very small dummy data. In real world scenarios you will have millions and millions of records. How can you plot? You cannot even plot a record on a graph, because that itself is going to take a lot of time. And so that is a part of exploratory data analysis, EDA, we call it EDA. And what the exact scenario, what the exact purpose of that EDA is to determine, let's say in this case, through EDA, basically exploratory data analysis, we can say that there are three clear clusters. So at a line here, we can say that there are three clusters. So what will be our output below this line, whatever is the output, the three clusters that emerge below this line, so that will be our separation plane, or that will be the clusters that we receive. Let's say we want five clusters. We'll go here, we'll go for something below this, we'll go for something below this. Let's say we want there's only one cluster. Through EDA I found out there is only one cluster. I'll go to the top level, and I'll set my margin over here, and at this margin I have only one cluster, which is the whole thing combined, all the data points combined. So it is generally analysis task to find out how many clusters are there. That there are a lot of steps involved in machine learning. One of them is data analysis. It is also a part of machine learning. Uh, you could say it is a separate entity, but it helps the machine learning engineers to make models. Exploratory data analysis is also a very big part, where you basically look at the data first in the physical form to find raw findings. So that is one part of machine learning that requires some visualization skills. Let's say you're using Python, you use Seaborn, or you use PyPlot, Matplotlib, whatever. So that is where EDA comes into the picture. So let's move on. Yeah. So the same data set that was provided to k-means, it turns out that hierarchical clustering, it performs way better on the same scenario, which is non-linear data. So the catch I want you people to take from here is every algorithm serves its own purpose. There can be multiple iterations of the same algorithm that perform better than the previous one. There could be algorithms that perform differently with different data sets. For this kind of data set, I feel hierarchical clustering is good. Maybe for another kind of data set, k-means is better. So it is really a task of trial and error, looking into the mathematics. That's why the mathematics and the deep dive is required to basically find out what algorithm will be the best one, or at least the most suited. I don't feel there's a best algorithm, but the most suited according to the task. So these are multiple clustering algorithms that performed on the data set. Let's say you have concentric circles here. So spectral clustering performs very efficiently. Agglomerative clustering, this is basically hierarchical clustering. It is just another name for it, which is called agglomerative clustering. Let's say this is a moon dataset. This is basically called a moon dataset, and you can see here again spectral clustering, ward, agglomerative, DB scan. They perform very well on the second type of data. So it is really the job of the EDA, the exploratory data analysis, to find out which algorithm will serve the purpose. If your data set looks something like the second one, you should go for spectral clustering, ward, or agglomerative, DB scan, anyone. If it looks like the first one, maybe you should go for spectral or agglomerative. Ward is not doing such a good job in the first data set. So just for a simple problem, this is a very common data set. You can have this data in your real life somewhere. For such a simple problem also, you need to at least look at 4 to 5 algorithms. So that is why machine learning is a very broad and a very big topic. We are just scratching the surface here. Okay, let's move on. Moving on to supervised learning. So if you remember, let's go back to the second slide. So now there are a few other topics under unsupervised learning, like dimensionality reduction. but I won't go over that. It is a little more advanced topic. It will be covered in the last few slides. I'll try to give you an example where this might come into the picture. So now we'll move on to the supervised learning. Supervised learning has two very famous or very popular tasks. One is regression. Anyone who is going through any course of machine learning or trying to at least research on it, he or she knows what regression is, what classification problems are. You might not know dimensionality reduction, but regression, classification, and clustering are very basic topics. So you might have come across them. So let's move to supervised learning. So what is supervised learning? Going with simple linear regression, you can see that there are a few data points on this graph, right? Sorry. Yeah. So there are a few data points on this graph, right? So now what the point of simple linear regression is, it tries to fit a line. It tries to make a line that goes through all of these data points or at least goes near it. Something like this. So now let's say I give you a new data point. Let me say what would be the value over here. So what your linear regression should do is give you an answer that okay, let's say at this point, this is the value, this is the y that I'm getting. This is the answer that I'm getting, whatever the prediction is. So what simple linear regression does is it's a continuous task. At any data point, I can find out based on the line what the outcome is. It works on a very basic mathematic principle, which is y is equal to mx plus c. So this is nothing but a form of y is equal to mx plus c. That's a simple line with a slope, right? Y is equal to m into x plus c. So what are the things here? M is the slope, c is your intercept, right? This is your y. So it works on the very basic principle of mathematics. Machine learning is a lot of mathematics with visualization, with programming, everything combined. So mathematics is a very big portion of machine learning. It is not necessary for you to know mathematics, but it is definitely a very helpful mathematics behind it. At least to me, it has helped in very in a very big scenario. Okay, so now what the linear regression will try to do is make a line over here. But let's say a data point that exists here. What will happen for that? It is a straight line, so it cannot exactly predict what the answer for this one should be, right? It is a straight line. It cannot bend. Y is equal to mx plus c. Is it a straight line with a slope, right? So that is where simple linear regression fails. Let's say there's a data like this, the actual line or the actual boundaries should be something like this, right? This is the right way for it to predict. If I say a data point that happens over here, it can predict that, okay, this is going to be the corresponding value. But if it was a singular line, it would have probably been something like this. So let me change the color. Yeah, it would have been something like this, right? So now what would have happened is if I say the x that is here, the x will fall over here. So now it should actually provide me a y that is supposed to come here, but there is a lot of difference between the answers. So simple linear regression is again not good for non-uniform data or non-linear data, basically, not uniform, non-linear data. It is only good for linear data, hence the name simple linear regression. So what can we do to solve this problem? You can go for polynomial regression. Simple mathematical topics, polynomials, simple linear equations, polynomial equations, ये सारा mathematics ही है. So what you do is you go for polynomial regression. What is polynomial? You would have seen, na? polynomial is basically apna y is equal to ax square plus bx plus c. This is one kind of polynomial. It is of the second degree, right? Similarly, you will have maybe, let's say, ax cube plus bx square plus cx plus d. Again, the same equations. So yeah, that is the basic mathematics that is again involved here. Machine learning may we write it the opposite way, because we start with the lowest order, we start with the constant v naught, and then we move upwards, because these are called as weights. We'll discuss about these in the next few slides. Right, so dot dot dot. So this is how the polynomial regression works. It is based on the polynomial equations of mathematics, basically. It works the same way how linear regression is supposed to work, but because it can have multiple orders of x's, it can fit into curves. So now this is where polynomial regression wins. It comes ahead of simple linear regression. But regression and in general machine learning topics have a very big problem. There are a lot of problems, but a very big and basic one, it is called as underfitting and overfitting. Now, what is underfitting and overfitting? It is as the name suggests. Now, let's say I have a curve. Let's say there's a point over here, there's a point over here as well, and there's a point over here. And let's say there's a point over here. Now, what if my curve goes like this? Is it a good curve? Is it a generalized curve? It is not a very generalized curve. It looks like a it looks like a roller coaster, and that is not a good curve. Your curve should be smooth enough that it can generalize all the points, that it can predict at least to certain probabilities. Like, let's say it's either 70% or 80%. So this is called overfitting. Overfitting is when your model is too inclined towards the training data or too inclined towards whatever the inputs you have provided. It calculates each and every small detail about the input and maps to it, and that is not a very good model. You need a pretty good generalization that is right here. Even if suppose I have a few outliers over here or here, they are not going to be too off from what the prediction is. The prediction will map something over here, right? So yeah, so it has to be a very general curve, and this is one of the simplest and the biggest problems in machine learning, which is underfitting versus overfitting. Will not go too much into detail, but I'm trying to throw a few jargons and terminologies at you. So maybe after the session, or maybe when you're trying to learn about machine learning, you'll at least Google these things and come across problems. You'll come across different solutions. That is only the way you can learn machine learning, is going across through experience and through whatever the problems you find. Overfitting, underfitting, high variance, high bias. These are just a few terminologies, jargons that will help you to basically overcome whatever the problems are there in machine learning models. So, apart from regression, there are certain models like SVM, which is called a support vector machine. Now, these support vector machines are also very good at differentiating linear data. As you can see here, what these support vector machines do are they basically try creating margins between the data. Let's say here there are multiple margins, you can see here, right? This is the first, this is the second, the third, the fourth. These are a few margins that could go across the data and differentiate them. I can have this margin also, which differentiates the data. These are a different kind of data points. These are a different kind of data points. But which is the best margin out of these? So the optimal hyperplane, this is called a hyperplane. Hyperplane is nothing but a boundary which separates the data points. These are just heavy technical terms put over there, but it is as simple as making boundaries. So the optimal hyperplane is the hyperplane. Let me use the word margin. It becomes way easier. So the optimal margin is the margin that is farthest from each of the support vectors. Now, what are support vectors? As the name says, they are the vectors or they are the data points that are used to calculate this margin. Initially, let's say I plot this margin. Whatever are the closest data points to that margin, let's say this is support vector alpha 1, this is support vector alpha 2, and this is alpha 3. So these are the support vectors that will be used to make this hyperplane. We'll not dive into the mathematics, but SVMs are pretty powerful machine learning models that are used frequently. Apart from regressions and all the other models, SVMs are very popular. So they are used generally in image recognition and text classification. So moving on to logistic regression. Now, logistic regression sounds like, not sounds like, it actually says regression, but it is a little different from regression. What regression does is it provides continuous data points. It provides you the answer for, let me move back a slide. So if you look at this, if I was supposed to make a polynomial curve to this, it provides me variable values. For the x I find here, I can get its responding y over here, right? Similarly, an x that I find over here, x is basically a data point. I keep saying x, but it is basically data point. I can get its value over here. So these are continuous. It is a line, right? Logistic regression is a classification problem and not a regression problem. What logistic regression does is it classifies the whole data into two subsets, right? Either it is true or false, 0 or 1. Either it is a yes or a no. So that is what logistic regression does is. So now how logistic regression works is, for the initial idea, you can just assume. So let's say this is a height weight graph. You people might know BMI index, right? What BMI index is. So what BMI index does is, based on your weight and height, it tries to tell you whether are you obese, or do you have are you overweight, or are you underweight, whatever is the scenario. So there are, let's say in this data, there is clearly a distinction that either people are obese or they are not. So this is a classification problem. Either it's a 0 or either it's a 1. So classification problem cannot be solved by linear regression, because linear regression is a continuous effort. What logistic regression does is, logistic regression is basically following this curve over here. I'll explain what the curve is. But what it does is, there's an optimal margin here, let's say 50%. What it does is, above this margin, all the values that I get are basically obese, and below the margin, all the values that I get are not obese. Now, that was a very high level overview that I've given. It is not just going to say that it is obese and this is not obese. It has mathematics going on behind. It has a lot of other functions going on, but a highly overview that this is what it does. Now, let's say we'll take another example of tumor size and whether it is malignant or it is benign. What do you mean by malignant? That means it is cancerous or not. Benign is an uncancerous or a non-cancerous tumor, and malignant is a cancerous tumor. So what we could do is, we could plot a curve like this using our newly learned logistic regression. Now what it does is, what I say is, h of x is basically our output. When you given an input, let's say this is my input data point, which is going to be x. Now what h of x is, it is theta transpose of x. Now what is this theta transpose? It is a very mathematical term, but on a high basis, high level basis, it is nothing but your features or biases. I mean, sorry, these are the weights and these are the features. The x is the feature. Now, what is a weight? As you saw, the y is equal to mx plus c equation earlier for linear regression. We were fitting a linear line through y is equal to mx plus c. Now, what is this m? We call it slope. The machine learning model calls it weight. What is this c? We call it intercept, and the machine learning model calls it bias. This is the bias, and the m is the weight. It is similar to the mathematics, but it is similar to the mathematics involved. But the thing is, notations are different in machine learning than they are in the mathematics. You can use the same notation. There's no issues. But this is a kind of primary school or high school notation that we use. M is the slope and C are the intercepts. In machine learning, we use bias and weights. Generally, instead of y, we have something like z is equal to w into x plus b. So here z is your output. Z, we can call it as y or h of x. Whenever I write h of x or I write y or I write z, anything except x, it is basically the output or the prediction. So now what Z is, it is basically multiplying the weights and the biases. And what these models do are change weight and biases according to the results and give you predictions. That is how the models work. They change these weights and biases and then they give you the predictions. What every machine learning model is trying to do is configure these weights and biases so that whenever it gives an output, it is closer to whatever the label is defined, whatever the task is assigned. Let's say I give you a data point which says that it is malignant, right? These data points are malignant. So now what it does is it is trying to adjust these weights and biases such that whenever I provide this data point, it is going to give me a value of 1 or a yes. So anything above 0.5 or the probability is 50%, anything greater than that will give me a 1 or a yes. That means it is a malignant tumor. Anything below it is going to give me a probability of 0, which is going to tell me that it is a benign tumor. Now, who does this? How does the computer know what weights to adjust, what to do, where are the brains behind each process? So, the brains behind each of the process is a neuron, or you can call it as a perceptron. We'll discuss in detail about this neuron and perceptron after this, but heavily what like basically what I want you to visualize is that you are giving in plus bias, that you are giving in this wx plus bias, and now this is going into another function called an activation function, which in our case is also known as the sigmoid function. And what this sigmoid function does is, in the case of linear regression, as you saw here, we had y is equal to mx plus c, which could give us varied values, which could basically not be ones and zeros, right? I have a range from 1.2 to 2 here. So either I could get a 1.2, I could get a 1.6, I could get a 1.8, I could get any value between these ranges, right? So what I want to do is classification. It is probability. It is not getting the results, or it is not basically getting a discrete value. What I want is a probability whether it is malignant or it is benign. To convert that distribution into the probability, what we do is we pass it through a sigmoid function. It is also called an activation function. So what this activation function does is it will map all the y values. Let's say, yeah. So sigmoid of, let's say, g of y, that will basically be 1 by 1 plus e over negative y. This is what the sigmoid function does. Instead of this y, we are going to put this wx plus b. So now what it will do is it will map all the outcomes to a probability distribution of something of this sort, where it is going to range from 0 to 1. So this solves our problem of discrete inputs that we were getting in linear regression. Now it is a task of classification. Either it is a 0 or it is a 1. That is what is demonstrated over here. This is called a sigmoid curve or a sigmoid function. Now, this sigmoid function, now once it calculates that what is the predicted value, I give it the data, it does all the calculation. Now let's say I give him a malignant tumor over here, right? But it predicts that the value is 0.2% or sorry 0.2 or 20% that it is malignant. So it is saying that it is a benign tumor, but it is actually malignant. We know it because we have the label data, right? So what to do now? What will the machine learning model do now? How will it improve itself? So the model improves itself the same way that we do. We learn through mistakes. We punish ourselves, not punish, but you can say we work harder. That is our punishment. That we are going to work harder. We are going to overcome the mistakes. We are going to learn from them. Now, how the machine learning model learns? The machine learning model basically learns through what is called a cost function. You have to pay a cost if you are wrong. That is what the basic scenario is. What this cost function tries to do is basically it will penalize the machine learning model if it is wrong. This is a very common cost function that is used. Log losses, it is called log of losses or log odds, whatever you want to call it. So generally you would have seen the log function, right? The log function looks something like this, where this is 1 and this is 0, right? We know that log of 1 is 0 and therefore there's the intercept over here, and the log of 0 is undefined or infinity or whatever you want to call it, and that's why it is going here. So now what this cost function does is, let's say the assumed value, the value that is true, it has to be 1. Let's say the tumor is malignant. I have to have 100% possibility, 100% probability that the tumor is malignant. That is what my outcome should be. But what the model gave me is it is not malignant. That it is 0% probability, or maybe let's say 20%, 30%, anything below 50 will be calculated as 0. So what will happen is, when h of x or my output is 0, it is negative log of 0, which is negative log. How does the negative of this function work? It is basically going to be something like this. This is negative log, right? We are interested only in the part where it is from 0 to 1. That's why I have drawn only that part, because we are interested in the classification. So what this function does is, now here, when the model says that it is 0, but it is actually 1, you can see the cost is infinite. When I say that the output is 0, but it has to be 1, the cost is almost infinite. It is tending to infinite, that is heavily penalized. Let's say I say it is around 30%. So it is going to be somewhere here. So the cost is going to come around here, because negative log of whatever the value comes is going to be matching here. So that is a heavily penalized value. So what it will do is it will penalize the model. Now let's say what the model said, it is 1. Yeah, it predicted it as right. So at 1, what is the cost value? At 1, the cost value is 0. So what the model will do is it will find out, okay, there is no penalization on me. That means what I've predicted is at least closer to what it should be. It is a true value basically. Similarly, if y was supposed to be 0 and it classifies it as 1, when I say it is 1, it means anything above 50%, it will say it is 1, right? So now the curve here will look something like this, right? So when it is 0 and it is saying 1, that means it should be heavily penalized because it is very wrong. It is completely opposite. So the more you move towards the right decision, the less you are penalized. And that is how the machine learning model keeps improving. It tries to reduce this cost. It is trying to improve itself. Now, who does this cost reduction? We have the formula over here. Okay. So mathematically, what this formula looks like, these two formulas are the same thing. This is the actual implementation that we use. This will map to the same thing that we did there. Let's say here h of x is the predicted value and y is the true value. Sorry, it should not have been y of x, it's just y. So h of x is the predicted value, and I say h of x, the predicted value is 1, whereas it should have been 0. So what will happen? Just try to put things into the equation. When y is 0, this term becomes 0. So this term is cancelled out. What is left here is negative of negative of 1 into log of 1 minus h of x. So which basically brings us back to this term. So when y is 0 and your output is 1, we come back to this point. Same way, if it is the opposite cases where it had to be 1 but it predicted it as 0, you will come back to this case. So mathematically in the computer, in the language through loss functions, we implement it this way. This is the actual equation. Now, don't get scared by this long, huge formula we have here. It is just this equation, the loss basically. And the loss is taken in account for each and every value. Now, the input points, the data we provide, let's say we have 100 data points. So for each data point, it will calculate the loss. Then it will take the whole cost function out of it. So the cost function j of 0, j of theta, sorry, looks something like this. This is nothing but the cost function we discussed earlier that is used to penalize the algorithm. So now what this cost function is doing is that we discussed earlier, that it is penalizing the algorithm. It is going to return a cost or a premium that the machine learning model has to pay if it is wrong. What we do is we use something called gradient descent. This is the actual mastermind. This is the person who is penalizing the model using this formula. Not only this one, there are multiple loss functions, there are multiple cost functions that we can use, but this is a pretty common one. That's why I'm explaining it using this. So what gradient descent does is it updates all these weights. You see theta of j here, that is nothing but in the case of y is equal to wx plus b. This theta of j is nothing but this w. Again, it is a difference of notation. That's it. This theta of j is nothing but this weight. It will try to basically change the weights in such a way that we get the best results, that we reduce the cost. Now, how it is doing that? Let's say we start somewhere around here in the graph. Now, what this is doing, this is the current weight, right? And this is alpha. Alpha is also known as the learning rate. It is the same as your hearing learning rate. Learning rate is nothing but how fast the model is going to learn. This varies. This is again a hyperparameter. All these things are called hyperparameters. These alphas, these thetas are called parameters, and the parameters are called hyperparameters. So if I try explaining each and everything here, it is going to be a very long topic. So just bear with me, just stay here. Alpha is a learning factor. You just need to know that it is called a learning factor, learning rate or learning factor. And what it does is it decides how quick the model is learning. So now what this part does is it takes the derivative of this slope, which means it is calculating the slope. Now, if you are aware with my basic mathematics, this is the positive slope. So when it is going to apply it here, it is basically going to be subtracting from the original weights. Let's say original weight was 5 and I got the result of this as 1. It is going to reduce it and it becomes 4 now. So it will be basically moving closer towards the minima. It is going to our main goal is to reach here. This is the lowest of the cost function that we can get. This is the least. Similarly, if we start somewhere around here, it is going to calculate the slope over here, and this is a negative slope. Now, as this is a negative slope, if we get a value of 1 here, negative 1, sorry, for example, this is going to add because negative of negative is going to become positive, and now what you're going to get is going to be 6. Basically 6, which will be moving forward. So the main goal of this gradient descent is to minimize the cost somehow, which it is doing using derivatives. It is all differential and integral calculus in machine learning. The brains behind machine learning is nothing but mathematics. So this will try to move it closer to the minima, or basically the lowest cost that it can get. Everybody wants cheap and good stuff now. Everybody wants to reduce the cost and get the best outcome, right? That is what gradient descent is trying to do. It is going to reduce the cost on itself. Now, where does all of this that we learned fall into the big pipeline? The basically what is used to basically make the machine learning models, or what the complete process is. So this is the overall pipeline. It starts with data collection. Any machine learning model, any problem you are going to solve is going to start with data collection. Once you have good data, once you get a structured data, what you're going to do is you're going to perform some analysis, or you're going to perform some pre-processing to make the data cleaner. Let's say I have a data set of car sales, and there are some missing data. Maybe in the month of January, I don't have the sales. Maybe it was a mistake of the database that was storing it. Maybe there was some human error, whatever it is. So I need to fill that data. I need to have good data. I need to have clear data. Only then my machine learning model is going to be a good one. Otherwise, if you train it on a trash data, it will become a trash model. If you train it on a data, if you train it on a good data, it is going to become a good model. It is as simple as that. After data preparation, we go for training the model. So all that we learned right now, all the topics that we discussed, I shall use the word discussed because I don't think we learned like the exacts of anything right now. It is just a mere discussion. So the training of the model, that is what we are doing here. So all these topics, SVM, linear regression, all this fall under training of the model. Whatever your model is, if my model is a neural network, it is going to be a artificial neural network. That is going to be the model. If it is an SVM, that is going to be the model. Now, what happens after we make the model? After we make the model, we are going to do some kind of evaluation of the model, whether it is returning the right results or whether it is returning the wrong results. Then we move on to the production pipeline. So this is how it works in the corporate world. This is the basic pipeline that we use. Most of the projects that I have worked in use the same pipeline, where we move it to production and then we keep retraining the model. It is all, machine learning is a very growing field. It is an ever growing field. The more data you have, the newer data you have, you can retrain your model. So this is the basic pipeline. So I guess there is it's already 6. So what I'll do is I'll try to show you a basic machine learning model. We'll not discuss all the details of neurons and hidden layers and convolutional networks today, but I'll show you a basic machine learning model. So just to give you an idea of what machine learning is. Okay, so you can see here we are using TensorFlow. I've already made the Jupyter notebook. If you are aware what a Jupyter notebook is, it is basically a system of cells where you can run each each code in a cell. It is very helpful for machine learning engineers, data engineers. We generally use Jupyter notebooks, and Anaconda is a very good IDE. So yeah. So I'm importing TensorFlow. TensorFlow is a machine learning framework. TensorFlow gives you all the topics that we discussed. It gives you library, it gives you functions for it, it gives you support for it, so that you don't have to write all the code manually. Similarly, NumPy is also a very basic and famous library that we are using. Now, do not worry about the syntax, but let's just say this is a machine learning model. Do not worry about the syntax. Let's just say this is the machine learning model. Just look at the first words. Okay, this is our model. Now let me run these cells. Yeah, so this is our model. Okay, just focus on the first words, model. Now what should we do with our model? Our model has two parameters, which are loss and optimizer, which we discussed in the slides. What is the loss? Loss is basically the cost function, the log loss we were using, that is going to penalize the model. And optimizer, what is optimizer? It is the one who's going to do it, who's going to use the loss to penalize the model, which was our gradient descent. So this is where what we discussed falls into the picture. The optimizer is gradient descent, and the loss is mean squared error over here, but commonly used one is log losses. You can just ignore these details over here, but just be aware that whatever we discussed is falling into the picture over in this line. So now what I'm going to say, this statement basically tells to the model that use gradient descent for your optimizer or for penalizing yourself, and use the loss function as the mean squared error. Now these are the input data points I'm giving it, and these are the output data points. Each data point is related to each other. That means whenever I give you an input of -1, I should get an output of -3. Basically, I'm trying to plot a graph here. Now let's say there was a new data point over here. Let's say it was 10. So what should it give me? It should give me somewhere something around 19. You can see here how it is working is it is doubling and subtracting, right? 2, what is the output for 2? It is 2 into 2 minus 1. It is doubling and subtracting 1. So it is 2 into y is equal to 2 into x minus 1, right? That is the output we are getting here. 4 doubles is 8, 8 minus 1 is 7. So there is some pattern in the data. Now let's try and fit our model to this data. Now what is happening here, it is performing all the steps that we discussed. It is going to take the input, it is going to calculate the loss, it is going to penalize the model, and it is going to send it back for training. So epoch is nothing but this one whole process. The one iteration is called one epoch, where it moves from inputs to the loss to back to adjusting the weights to calculating the loss, everything. It is one epoch. Similarly, we are performing somewhere around 500 epochs here. And now our model is basically trained on the small data set that we have over here. But it is very quick to recognize patterns, right? So when I try to say that for 4, what should I get as the output? 6.99, yeah, very close to 7. Now let's say something that is not in the data set, that is 10, let's say 10. We can calculate it from the pattern that we recognize that it should be somewhere around 19, right? Let's run it. Yeah, we get 18.97, very close to 19. So you can see the power of machine learning here. 10 was not included in the data set, but from the pattern that it found that it somewhere relates to this function, it is able to at least give you a very good probability or a very good estimation of what the output should be, right? I'll show you a higher, basically a upper level example. This is a very common data set called as fashion MNIST. Now, what this fashion MNIST has, it has a few small images. Just don't look at the syntax. Just hear me out. Just follow me. Now, ignore all whatever is happening. Just ignore. So it has these small images of things like shoes, t-shirts, shorts, jeans, and stuff. It is the fashion, as the name says, it is a fashion data set, right? So now, what our task is, given an image, I need to tell whether it is a shoe or a t-shirt or a jean or whatever it is, a pair of jeans basically. So now this is my model, this is my machine learning model. There are a few more things that have been added, but due to time constraint I don't think I can cover them in this session. But just look at the model, and now when we are training the model, you can see here I've provided a few more fields like ETA, the loss, and the accuracy. You see what the model is trying to do. First, the loss was coming as 0.5. It is trying to reduce the loss. As you see, the loss is decreasing. As the loss is decreasing, the accuracy is increasing. What the model is trying is, it is reducing the losses and it is improving the accuracy. It is doing the all the things that we discussed, all the penalization, all the gradient descent in the background. And this is what the beauty of TensorFlow is. Within a few lines of code, I can make a basic machine learning model that is able to classify whether this image is a shoe or a jean or whatever it is. At the end, we found out that it gives me an 89% of accuracy, right? Now let me try and test it on some unknown data, right? On the unknown data, it gave me an accuracy of 87%. That means it is 87% capable to find out whether it is a shoe or a t-shirt or whatever it is. So here you can see the power of TensorFlow. Here you can see the power of machine learning. That within a small span of time, it is just a few lines of code, and you can do things that humans can naturally. Machines can't do it naturally, but you can make them perform these tasks like classification, regression, all of these. Uh, so yeah, I hope you are not bombed and everything. And yeah, let's move on to the Q&A section. I wanted to discuss the CNN, but we are well over the time limit. But if you have any questions, let's move.
So, hello everyone. If you have any questions, you can ask now.
So thank you everyone for joining. The session is over now.
Guys, you may leave.